Right, so we are live, Attila. So why don't you introduce yourself and what we're going to talk about? And there's about a 60-second delay on the live feed, but I'm sure there's people out there all over the world listening.
Oh, it's because the light is behind us. Okay, great. Hi, everyone. My name is Attila. I am from Serbia, and it is the middle of the night here, so that's why the lighting is a bit odd. But anyway, I'm going to talk about the MathBig package. I've never talked about before, so it's going to be fun. Let me try to share my screen first, because okay. So I'm going to try and share the entire screen. Move this away. Okay, here we go. So can you guys see the slides?
Yeah.
Yes.
Okay.
Yes.
Okay, great. So let me start with the MathBig package, and let me start with just a usual example, which is, let's say that you get an assignment, and we want the Fibonacci numbers, which is just the usual school example. So you make a get request, and you want the 37 Fibonacci number, for example. And then in Go, this is surprisingly short and surprisingly fast, and we can just run this. I'm going to run this right now just to play with the server and have. Okay, so sort of works. Let me see. 37. Yep. We get the results. I've done some benchmarks earlier, so it's relatively fast. And so we get about 500 nanoseconds for a recast. And first of all, our very first problem will be that the 93rd Fibonacci number is, of course, it overflows the int. So we want to use something like an arbitrary precision library that would handle this. And there is one in Go, which is the MathBig package. And it's surprisingly simple, so there we only need to change these 3 lines, and our code will already work. So let me go to 93. Okay. So we get big numbers that don't overflow, and I should just, for the sake of it, play with this a little. Yeah. That doesn't look as nice as it would in something like Python, where the built-in int just doesn't overflow. It's long enough, but it's still simple enough. So I'm going to move on quickly. Let's say that we want more than one number, because we don't want that many round trips, and we want something that is, we want a result that is JSON encoded. Now, the parsing of the URL is going to be a bit more complex, so I'm just going to leave out all that complexity and show. And in this result, I'm going to encode a splice of numbers to the response writer. So W is the usual HTTP response writer here. And instead of one integer, we are returning an array, or actually we are returning a slice of big ints, and it takes fairly longer than usual, but it's still okay. And I should actually go back here just to show that our original implementation, the one that used built-in int, took about 500 nanoseconds, and so it's a big int is about 10 times slower there, which is reasonable, provided that we get the arbitrary precision there. So we get the batch results, And our next goal would be to try and make this faster. And the first thing we would try to use is, well, instead of calling Fibonacci every time, we should just iterate here and add the number. So here the problem was that here we do an iteration to 12 and then to 13 and then to 14, and that's why this takes so long. So obviously we will try to avoid that and just stuff all the big ends in this slice and return one slice. Now the problem with that is I'm going to run this already. So if we go 12 to 18, we don't get the right results that we would expect. That is because we are returning a slice of pointers. And our problem with the pointers is that as we keep adding, we are changing the values. So the pointers that we receive, the values where they point to are changing. So when this function returns, all of these ints will be incremented, and this is obviously not what we wanted. So we will change this now to use objects, just plain ints instead of pointers. And I can show you this, but this is still not going to work, and we will still get the very same results. That is because we keep mutating these objects, and as we increment them, even here, when we take a copy of them, so when we append a copy in this slice, the copy is just a shallow copy, so it will still contain the slice of words, which is where the big int contains, so to speak, is digits. So this is still not what we want. So what we can do instead is just create a copy, and this new int.set, this will create a proper copy of the big integer, which is a completely new big int that we can use now. As again, somewhat faster because we don't have to do that many iterations, but it's still not very good because we are returning a whole bunch of numbers just so in the end we could encode them once. But we've already we improved the speed not twice, but at a factor of something like, what was it? It was 23,000, now it's 16. It's a bit more than half of what it originally was. So what we can try to do instead is, ideally, we just want to start with one number and reuse that same number, and we simply encode it every time when we need a value. So this next implementation would take a writer, which will be our response writer object from the NetHTTP package. So we start iterating. I added this shortcut, so if there's nothing to write, we just don't write anything, just to make things simpler. So here we're not even using JSON to encode the numbers. We start iterating, and when we want to print out values, we simply write to the response writer. So we write the A here, which is a pointer, and in the next iteration, we're going to use we're going to reuse this very same number, but it's fine because what we already written to this writer is in there. So we don't need more than one value. And this is the point that is often the case in when you're working with Go's MathBig package, because it's just something that I find that comes from Python and Ruby and these languages. So where you would want something where, for example, you would want a list of numbers in Python, you would simply create a list of numbers, or or if you need consecutive values, because it comes intuitively that numbers are immutable. So just like in Go, in something like int64 would be, so if it's not a pointer, yes, it would be immutable. And in Python, if we write something where a equals b plus c, so just forget that I wrote this in the Go code. So let's say this is some Python code. In Python, this assignment would be, this assignment statement would just take the expression on the right, evaluate it, and assign it to the value on the left, assign its value to this variable on the left, and that would effectively create a new copy every time. So because in languages like Python or Ruby, you don't have a way of mutating your int. You're always creating new copies. It is a bit slower, but it's safer, and it gives you this intuition that you are free to create just as many copies as you want. Where in Go, you can do that with the set, with what we do before, what we did before, like this. But it's not the best way, because you don't need them. It's because in this case, and in most cases, you need one number at a time, and you can just deal with that number. So we did improve this case where when we just get a few numbers, what about it's now about twice as fast. And if we get more than those numbers, it's actually going to be more than 5 times faster, which is still not that much improvement, but it also uses less memory because we are not returning the entire slice. So a few things about the big int, and this is not specific about the big int. The MathBig package also provides another type. Which also implements mostly the same interface, which is the rational type, which represents rational numbers mostly. This can represent arbitrary precision numbers. Obviously, we can't print them out, but anything that you can represent as a rational number, you can put in a rational, and the rational number under the hood is basically just 2 ints. The 2 ints that hold the value of the rational. So what I'm going to talk I'm going to talk about a few good things about the big int, and one of them is that it implements the format.formatter interface, which, if we go back all the way to this slide, no, the first one. So here we used integers, and we printed them to the response in a very simple way. We just used the format.fprintf function, and the %d would just print out the digits of a number. And when we changed our function to return a big int, we haven't changed anything, and it still worked. And it worked because our return value is a pointer to int, and the integer pointer implements the format.formatter So we can use it. We can use it just like an int with the format package. It implements a few encoders and decoders, most notably JSON, which we already used in the example. So it implements the JSON marshal and unmarshal, the text marshaller and unmarshaller, and the Go binary encoder and decoder. And so the rule of thumb is whenever you need to communicate with external services. So if you need to plug this into an API, like our example, you would mostly be using the JSON, especially if you put this in other structs, because JSON is just easier to work with, and it encodes and decodes just fine. But there's one issue with the JSON, with representing numbers as JSON, is that it is generally slower, because the internal representation of the MathBig package is it is a slice of words, and words is just a word is just an integer that is native to the architecture. So my architecture is AMD 64. So for me, a word would simply be an unsigned 64-bit integer. And the way the math package holds the data of the integer is it simply has a slice where every element of the slice is a word. So in fact, it is keeping the data in whatever base is native to the native to the operating system or the architecture of the Go compiler. Now, the JSON encoding and decoding is base 10, so the base 10 conversion can usually take much time there. And if we don't need to communicate with external services, if all you want is, for example, just catch the number, if you have a number that you want to catch in memcache or store it on disk, by far the fastest way to do that is with the Go binary encoder or Go binary decoder. And as a good example is a good example would be the number 10 to the 100 millionth, which is a number that is roughly it's a number that takes roughly 50 megabytes of memory, and writing it out as JSON and takes at least on my machine, it takes a couple of minutes, and encoding and decoding with Go binary, it just takes way less than a second. So if you have to work with numbers that are just over a few millions of digits, and the best way to speed things up is just to have one copy and catch it somewhere, either on disk or just in memory, and then whenever we need to work with that number, we just take a copy of that, and that is mostly fast for whatever we want to do. So we only need JSON. We only need the formatter if we really want to output data, which is mostly useful for debugging. We need the JSON if we want to communicate to some other service, mostly some other languages, and we need the Go binary encoder and decoder if we just want to cache something in memory. And one thing in particular when communicating with other services is, other than JSON, it is also a lot faster to just use 64-bit encoding because or basically any encoding that is power of base 2, because that just gets decoded a lot faster. Because, and it's not just for Go, it's also for if you're communicating with a Python service or a Ruby service. A Python service will definitely consume base 16 data, for example, just hexadecimal integers, much faster than base 10. So a JSON marshaller is nice and useful for a generic interface, or something like when we want to use numbers, or when we want to expose an interface that should be generic and we don't have control over the other parts. But if we are communicating, let's say, if we have a Go app that generates some numbers and a Python app that consumes those numbers, or the other way around, the fastest way to work with them is to just use base 16. Okay. And there are a few ugly parts, and there are people who critique the MathBig package, mostly because it's a package, because you have to do things like this. This is ugly, I know. And what in Ruby or Python or in languages that even Clojure has built-in big integers and arbitrary precision integers, and there you can just do powers or multiply, or basically all the operations that you could do on a built-in integer you can do on the big int. And that you can't do in Go because you can't extend a language like that. What you can do is just use the functions. And there are a number of things that can help you with that. So not all the code will end up looking ugly, but it's one of the side effects that if you write arbitrary precision if you deal with arbitrary precision numbers in Go, it will sometimes look ugly as hell. So one thing to be careful of is that the big ints are mutable, and not just because we are working with pointers, because that's one, but also because they have a copy of the underlying array, and even if we create a shallow copy, the array will still point to the same. The slice will still point to the same underlying array. So if we modify one int, it will modify the other one. So that's why we have to create copies if we have to. But the best is just not to create copy if we don't have to, and replace if we can. And one example of that is when adding. Because in languages like Python, when you add or multiply, you evaluate the expression, you create a new value, and you assign the new value to a completely new integer, because they are immutable. It is something that may come intuitively, but it will be slower, because it will just have that will end up in more memory allocation. So this code, the bad function, it does almost the same as the good one, except the bad one will not touch A and B, and the good one will. The good one will basically overwrite A. So if you need a copy, then you have to use the bad one. But if you can somehow avoid needing a copy, then it is always just the best to use to replace one of the arguments. So if we want to multiply, if we want to add, it's just best to to take one number that we usually don't need after the equation and just replace that. And it's conventional to use the first argument as the receiver. So if we want to increment a by b, we usually do a dot add a and b. Oops. And it even used to be that it was faster. At least I read that. And people were saying that if you do it, this will be slower because there is a fast path that checks whether the receiver is the first argument or not. And I vaguely remember that being the case, but last time I checked, which was today, I couldn't find this anymore. And I run a couple of benchmarks, and it doesn't seem to be the case anymore. So it is a convention to always replace the receiver with the first argument, but it doesn't seem to be any faster. So I don't think it matters. And one example of this, so one example where you should always prefer replacing over returning new values is, for example, a common case when you need to generate prime numbers, or basically any kind of numbers that you need to consume. And a very common scenario is that you have a function that you call and it returns you a channel, and that channel will return you integers, big integers, and then you do something with those integers. And because you are returning ints in the channel, and you want to be sure that the other coroutine that modifies those will not impact the coroutine that sends them on the channel. In other words, just to avoid any sort of race conditions. When you send big ints in a channel, you usually create a copy, which again, more memory allocations. So it's often it's a better pattern that instead of creating a channel and sending ints, it is just better to have something like a struct that you can, instead of iterating over, it's similar to have an interface that is similar to the scanner interface that scans the files of a line, where you instead of ranging through a channel, you call a function, and every time you call a function, it would just increment your number. So it would increment the same number. So in the case of prime numbers, if you want the first 100 prime numbers, the most efficient implementation would simply keep one prime number, and every time you call a function, it would increment that same prime number and just give it to you or return it to you. And whenever the receiver actually needs a copy of that, it should just make a copy. But when a copy is not necessary, or when the receiver doesn't modify it, it's faster to just not create many copies. So to keep as little of them as possible. And one way to figure this out is to run the Go profiler and generate the graph and see where is most of the time taken in your program. And in most cases, it will be the allocation, and in many cases, the allocations come from the MathBig package, and most of the time, the allocations are there because when you do an operation, it has to create a new variable because you are modifying you are replacing one. Oh, sorry, because you are not replacing one. Because instead of replacing one, you have to create. When you're creating a new one, it has to allocate the memory, and especially when working with numbers that are over a couple hundred digits long, it's most of the times the memory allocations are the bottleneck. And to get slightly faster than that, there is a drop-in replacement that uses the GNU multi-precision library, which is used by Python as well. And the fastest libraries out there are the fastest arbitrary precision libraries are all built on top of this multi-precision library. So the way this works is you simply import it instead of MathBig, and it just works. Not everything works, but there are a few corner cases, but most cases will just work. And the author run a benchmark that I didn't run personally. I just take this as granted. I did run this, and I did run. So I did try using the GMP for the example server in these slides, and in most cases it is just slower, and in some very rare cases with numbers that are around 100,000 digits or 1,000,000 digits, in those cases it's faster. But in our cases with the small number examples, they were just slower. And the slowness mostly comes from Seago, because it has to do the round trips, because Seago is simply a binding. So for big numbers, it is actually faster. And in his example, anything that is bigger than 1,000 digits is already faster with GMP. But yeah, that's just addition and multiplication. So it doesn't mean for all cases, but it is most likely the case. And that's it.
All right, thanks, man. I've got one question. Can you hear me?
Yes, I can.
If you have to work with money in Go, you can't be using that float 64 really, right? That's not enough precision? Or is that enough precision to work with monies?
Float 64. Well, Float 64 will most of the time work with money. It's not it's not the precision that's I mean, usually the precision is fine. It's just your problem is often that the operations are not as well defined. For example, addition is not commutative on float 64. And also, if you have a whole bunch of small values, adding them together would result in different values based on the order you add them. So if you take a whole bunch of very small values and add them together, you will end up with something big. But if you take one big number, something that is let's say a couple billion, and you keep adding very, very small numbers to it, it will just not change, because the precision is dynamic. So in that case, yes, if you have something like that, then you would one of the easiest way would be to just use the MathBig package, but you wouldn't use the int, you would use the rational one. But there are other ways. So the thing with the MathBig is, if you are worried about speed, there are very often cases where you can work around it, and where you can just, instead of simply using just big numbers, you can very often just avoid having to use big numbers in the first place. For example, if you're worried about the precision and overflowing, you could just make sure that you order your when you're adding. So let's say you have to add the whole bunch of accounts and to get the full balance. If you go and add them up sequentially, all of them, you will most likely get a result that is off by something. But if you add them in a way where you group them, for example, and let's say you group them in small shards, you just create some shards, and you add those small groups together, and then you add the groups together, and you continue that, then you will get much less error. Like one other example is often you just need to work with very big numbers because you are working with huge powers of 2. Like when dealing with Mersenne primes, which are 2 to the power of big number minus 1, or just Mersenne numbers. It is easy to work with them with the MathBig package, but it is often just easier to not have to work with big numbers in the first place. So if you can somehow avoid that and just do the math on paper and then just do the powers of 2, just keep the powers of 2 and do or if you can work modulo some number that fits a 64-bit unsigned integer, then it's going to be way faster. So as much as I like working with the MathBig and with big numbers, it is often just, it makes more sense to avoid that if it is possible.
All right, great, cool. Anybody else have any questions? All right, man, I think you can get some sleep now. I really appreciate you staying up late.
Okay, thank you guys.
Bye.
Bye. Good night.
Bye-bye.